Okay, so let's get started, I guess. I'm Murat Demirbas. I have been in distributed systems for 28 years or so, and I have been doing TLA plus more actively for the last 15 years. This talk is about thinking in TLA plus and doing modeling judgment for system design. So the premise is this, right? So let's acknowledge the big elephant in the room, LLMs. In the age of LLMs, now the syntax is no longer the bottleneck for learning TLA plus. So this is accidental complexity, and it's going away. You know, syntax has never been TLA plus's strength, and a lot of people complain that, oh, you know, TLA plus is cryptic, I cannot remember how it works every time, etc. But this is going away. But the intrinsic complexity remains, and the intrinsic complexity is about modeling judgment, right? And this takes a long time to develop. You develop it basically through osmosis, from your advisor, from seeing other models, from working with others. And if LLMs take away this, it's good news and bad news. Good news, people can start writing models. Bad news, they don't understand the models that they write, and they get zero value out of the models. Because the value of the model is that it's a thinking tool. It shapes how you reason about systems. I mean, TLA plus is not a push-button verification tool that you bolt at the end. It's a thinking tool that shapes how you reason and understand your system and evolve your system. TLA plus's value is in this perspective shift. Engineers think in code, control flow, local state, but TLA plus forces a different mode of thinking, which is mathematical, declarative, and global. You must specify what must hold, not how to achieve it. And this comes very counterintuitive to people who started coding with imperative languages. And when I was teaching TLA plus in my distributed systems classes starting from 2014-ish, and I went with teaching in Pascal to be more user-friendly to the students. These are second-year master's students and some PhD students. And some of them would write Pascal models that look like Java, because Pascal looks like more like, not the TLA plus syntax, but more imperative. So the shift in this thinking is the actual value. And today I'm going to talk to you, this is what I observed over many industry projects. I'm going to list about 8 that I used TLA plus, or in one case, I observed TLA plus used and I helped nominally. The TLA plus works because it changes how you think. And after 15 plus years of using TLA plus, I now think of TLA plus as a design accelerator. So in this talk, I'm going to give you the 7 mental models for thinking in TLA plus. You can follow my talk. We are in slide number 3. It's highlighted through this top menu. So this is Beamer. So I think these are the thinking patterns behind effective TLA plus use. This is my first attempt at it, and hopefully this will make other people to chime in on this discussion, come up with their mental models so we can create some value and tell the developers to say, okay, this is how you should be using TLA plus. Just getting a LLM, generating a model doesn't make that your protocol is correct. Your protocol, I don't know, you may not be even using the correct invariants, etc. Let's teach you this, and then we will, then you will be able to get more value out of TLA plus. When I joined MongoDB research, 2024, I did a workshop, TLA plus workshop for MongoDB as part of their hackathon week. People are free to explore things. It was a productive thing, but most of our time was spent on the, teaching the TLA plus syntax, trying to get them write a simple model. Now we are going to attempt it this May again. The LLMs are going to help them write these models well, so we are going to give them even hands-on project to model, but we are going to first teach them about these mental models to equip them with the right way of approaching the modeling, and then we will see how it goes. So I'm going to report back to you, but this is how I intend to reteach that TLA plus workshop at MongoDB. And as I mentioned to you at the beginning, this is generally acquired by osmosis over years of practice, but let me try to make these explicit and actionable, and I will welcome your comments on what is missing here or what could improve things. Feel free to ask questions during the talk. And I have a 1 hour, well, 50-minute slot, so. Okay, the first mental model. When Les Lamport gave his 2019 St. Petersburg talk on how to win a Turing Award, I think he had this verbatim. He said, how to win a Turing Award? Abstraction, abstraction, abstraction. So that's what I made the title of the talk. What is abstraction? Abstraction in Latin, we are in Rome, we are in Italy, it means to cut away. Okay? So omission is the default. Add something to the model, only when leaving that out would break your exploration. If you weren't trying to write a message protocol, you don't have to write the messaging explicitly. Go global shared memory. Don't model the network or messages, for example. That's what abstraction is about. And then abstraction is also about when you are writing, focusing on a problem, do a cross-cut slice of the system to carve the protocol you want to investigate. Ignore other things. Make the environment, make them part of the environment, okay? So you should be asking, what is the behavioral slice I care about, and what can I safely ignore, okay? And this is something I intuitively think is the case. I don't have data on this. I want to actually explore this more. TLA Plus provides a lot of value because it gives you tight feedback for to accelerate your design experience. I don't know of any tool like this, right? Typically, how do engineers learn design? They are given a simple component, they design, they see by mistake, but 2 years pass. The guy tried to implement and get this into production. They see how it fails in production, learn something. They also attend a lot of meetings. They see how other designs go work. In TLA Plus, you can write your protocol. You think it's correct. The model checker will tell you how you messed up, and you were, of course, how did I not think of it? Because concurrency is hard. Evolution did not endow us with concurrent reasoning abilities. And that's why we have TLA+. It has tight feedback loop to accelerate the design experience, but the way to milk it is through abstraction. So let me go concrete. In 2018, as part of my sabbatical, I was at Azure Cosmos DB. They asked us to, the Azure Cosmos DB has 5 consistency levels, and it confuses the users, developers, about how these work. And we said we could write a TLA plus model to explain them, because there are documentation, but English language is ambiguous. So we decided to write this external facing model of the distributed database. The anti-pattern here would be to model the distributed database engine, which first would piss off the Microsoft guys, because they don't want to talk about the protocol distributed engine they use inside Cosmos DB. They want to show what it provides. Secondly, it would cause state space explosion. So what did we do? We modeled the history as a log. This is the abstraction we use, okay? The database gives us a log, and then there are different nodes of the database, different regions. They may have separate logs, but we also wrote a sort merge function that captures the replication internals at 1,000 feet or even 10,000 feet, because it takes different logs, it merges them into a single log, and this is what the replication does when it replicates from a master, etc., but it captures this by this sort and merge function over history as a log. And the read index captures consistency, and you can see the 5 consistency levels as predicates over operation history, and this gives the users an understanding of how these 5 consistency levels compare. So this is a URL. You can click on it. It goes to my blog post on this, where you can click on it and get to the model. Later in 2024, I think, Marcus Coupe and Finn Hackett, they redid the model, and they even used the model to do conformance checking to catch some bugs, explain some bugs in Cosmos DB. Okay, that all apart, what is the lesson from this experience, industry experience? A model does not have to capture everything. It just needs to capture the behavior that matters. And that's all about abstraction. On this one, the second experience I want to talk about is Amazon Aurora DSQL. This is a distributed SQL service developed at Amazon. This has been released in 2025. I was working with that team from maybe it released in 2024. I worked with them from 21 to end of 2023. This is secondary index. And one engineer was tasked to build this component. In Amazon, you always write a design document, 6-page design document in Word, not Word, but whatever. And then you get it reviewed. He wrote the design document, but then he finds a, corner case. He's a smart guy. Before writing the code, he wants to patch it. He patches it, finds another corner case. He doesn't have code, but by thinking he finds these corner cases, his 6-page document become like 18 pages, etc. I was visiting Seattle, and then I had an afternoon free. I met with him. I said that, my intuition says that this is not a very distributed problem. In one node, we are creating secondary index, But the fact that your design exploded means that this is a complex design. There is concurrency still involved, even though this is not distributed. So let me try to write an initial TLA plus model of it. Again, I use the same trick from Cosmos DB modeling. Model the database as a log of operations. And I wrote an initial TLA plus model. This was Friday afternoon. Over the weekend, because this guy had been working on this for 3-4 weeks and frustrated with the design, he took my TLA plus model, he wrote variations of it, saying that, oh, this might be another interesting way to design it. This might be another interesting way to design it. And on Monday, he had variations written. So the TLA plus, basically writing this in TLA plus, forced a perspective shift. It forced him to think declaratively instead of patching corner cases. And the experience from this is that don't grow the design by patching, search the practical solution space. I'm going to revisit this in refinement. Any questions so far? So I talked to you about 2 experiences, one in Cosmos DB, my first industry experience, 2018, and one, the Amazon D-SQL from 2023. Okay, shared memory. I don't have industry experience to report on this because this is pretty basic, and this actually forms the foundation that you build the other things I'm going to talk about, monotonicity, invariance, refinement. So embrace the global shared memory model. What do I mean? The computation model of TLA plus is extremely simple. Program is a set of variables which the values of each variable, Cartesian product, gives you the state, okay? And so program is a set of variables plus finite set of guarded actions. What is an action? Action is the late Sir Tony Hoare's triple. State assignment to a subset of variables, state prime, the next state. And you can put a guard on it, and that's all you need to know about the TLA plus computation model. It just atomically executes this guard, state, guarded action, guarded assignments on variables, and next state. And then pick another action and do it again. That's the beauty of it. This is the most minimal way to model. It hides message passing, but it's okay. Later, you can refine your model to a message passing model. So be frugal with variables. Each one exponentially exploits the state space. And beauty of GSM is it gets you to the state-based thinking, which is invariant-based thinking. Safety and liveness become compact predicates over the global state. Okay? I'm going to skip through the rest of the thing, saying that, okay, what about local variables? Node i's version of what is what I, okay? Global variable becomes the array, local version becomes the index value of it. But the rule is I'm going to visit, next talk about this rule, monotonicity and local invariance. Keep the localish guards and local variable assignments, and there would be a refinement possible for the message passing model. And I think this would be easy to teach to engineers, okay? When we were teaching generally through the syntax, maybe we didn't have enough bandwidth to focus more on this, but now when we teach like this, maybe it would be easier to teach. We just teach the mental model. Of course, the trap with the global shared memory modeling is that it's easy to write guards with illegal knowledge. Okay? What does this mean? Illegal knowledge mean? It means non-local predicate, non-local reach. You can easily write a guard that looks at all other nodes' values, a global guard, and this won't be acceptable for a this won't be acceptable except for a first model if you are doing refinement. You need to make your guards to only work with what a real node would actually know. So audit every action. I made this stupid mistake for least guard modeling later, which I'm going to talk about in refinement section for a rough lease protocol we developed. I sort of, when I'm doing the TLA plus actions, I was careless and assumed, okay, the other leader, a new leader that might have stepped up, would know the index at the previous leader. So that doesn't work. But that was still good enough for me to get the intuition about how do we make rough leases so that we don't use Paxos leases, because Raft is a stricter protocol, and why don't we exploit the strictness of Raft to come up with a better lease protocol for Raft? The way we later patched it to say is, I still know what your index is, the later commit index. Your index is from there, and it could be more, and we call this limbo region, and I may reject some queries about that region, but I can still serve some reads from that before that, and I can still provide availability during leader handovers, even when your lease does not expire. So, but my mistake was I didn't audit my first model for this knowledge. We caught it later. Okay, so this is part one of that, refined to local, monotonic guards. What is the part two of that? What is the monotonic parts? Use stable monotonic or locally stable predicates for guards. I'm going to talk more about this in the next slide. The idea behind this is, if the guard remains true despite another node's action, this means that you need less coordination. Otherwise, you would need locking to make sure, okay, for me to execute this action, you don't change your state for a while. How do we do this? We do something like dining philosophers, hygienic version, to have a local neighbor locking, but that means more coordination and more complexity. So refine your guards to make it monotonic. Okay, let me generalize this. Basically, distributed systems gurus who write distributed protocols, who have been in the field for more than a decade, actually more than maybe 2 decades, they know that for doing coordination efficiently and safely in distributed system, the insight is almost always to transform the problem in a monotonic one. You got to keep things moving up for some definition of up. Okay? This is the key to keeping progress in a distributed system. And the beauty of this up is, it's hard to find it, but when you find it, that knowledge is preceded at all nodes, and you don't need coordination for that knowledge, you just mute that knowledge. Okay, I'll try to give an example of it. Of course, Paxos. I'll keep referring back to Leslie Lamport's 2019 talk, where he talked about Paxos derivation in retrospect, because he doesn't remember completely how he derived it in the first place, but in retrospect, the ballot monotonicity, it makes the voting guards locally evaluatable, okay? And often you use a similar trick. You use monotonically going up a ballot or counter kind of thing. And then a higher one preempts a lower one. So even if you try to make progress, you know which one is the more recent one. Time is also a good monotonic dimension. But it's an art. This is an art. Among all of these, I think this is one of the most hardest one. This requires a lot of experience to come up with this. Secondly, I would say this is also tightly connected with the abstraction thing, because noticing that thing is the art of abstraction. The log, modeling the database as a log, you can also see the monotonicity of that. The log only grows by append only. See? And the other thing would be the invariance. And if you look at the LLMs, just one minute. If you look at the LLMs, there has been a paper, Sysmo Bench. They looked at using LLMs to derive TLA plus models from code. They had to give them the abstraction because LLMs are not good at writing the abstractions. They are good at syntax, not abstraction. And they also had to give them the invariance. They are not good at doing the invariance. Monotonicity, just out of the picture, Igor.
So this idea of monotonicity, I also have seen it in many consensus algorithms, obviously, right? But like, does it mean that we can define a ranking function over this?
Say this again?
Does it mean that we can define a ranking function over the state space somehow, and that gives us termination, all these things?
Right. You're right. I think this is related to the variant function that we use for liveness reasoning, but maybe not always. I think it's more, it's even more general than termination reasoning, figuring out a monotonicity dimension that you design the protocol around. I cannot, I need to think more on this. And this is hard. This is hard. You need, I think, maybe 2 decades and a lot of hands-on action on protocol design to figure out for a more complex protocol what would be the monotonic thing. I mean, Lamport's Paxos ballot monotonicity is brilliant. That's, that's how he got the Turing Award. It's a brilliant insight. And, but for different domains, what is it? Generally, it's some kind of contour, some kind of, this ranks higher, as you said, but it's more general than just liveness reasoning, I believe. Yes, Mamun.
When you talk, we have the impression that you do the things in a sequential way. You have talked first about monotonicity, then about invariants, but sometimes in order to validate that your guard is stable, you need to know the invariant.
Yeah.
And so I think that you have to go between the 2 levels to come with such stratification, because I don't think that...
Yeah, I agree. So these are the art parts. Hard, hard, hard. Basically,
and it is not sequential. More or less, it is until the end that you know the different parts.
Yeah, this is the thinking part, and I don't think LLMs would be able to replace this. LLMs do pattern matching. If there is similar exercises, examples, they would help. That's actually the last step. Share your models so that we train the LLMs so they can write better models. Yeah, I agree. So basically my thinking about writing the guard more monotonic is, stable is monotonic, right? If you can write your guard to be something stable, if it doesn't change, you can execute that action anytime. You don't need coordination for that. If your guard depends only on local variables, you can say, okay, I don't need to coordinate for evaluating this guard with any other, so no coordination is needed. Or guard is locally stable. Your neighbors did something, the ball is on your court. If you haven't done something, this invariant would not be falsified, or this condition would not be falsified. That's also locally stable. So this is what I have, unfortunately, at this point on thinking monotonically or helping design tips for monotonicity. But otherwise, you would have a fast action, which would require more fresh, non-local action, and that means some kind of locking to coordinate with your neighbors. And that makes the protocol slower. Okay, invariance. Derive good invariance. Invariant is the most distilled understanding of your protocol. Invariance scaffold the exploration of the design. It scaffolds composition, fault tolerance. For example, when you know the invariant, you know that a fault can throw you outside your invariant, and the recovery would mean writing some correction actions that gets you towards the invariant back again, which is closed. But yeah, and the invariant also scaffolds testing. Igor talked a bit about it. I'm going to also talk a bit about this. So the anti-patterns. LLMs write terrible invariants, unless this is a model that they have seen before. Right? So they would write trivial invariants, like type OK or something. And then people also write, novice people also write terrible invariants, which I also am a novice person when I'm looking at a new domain, because I don't understand it. Invariant writing needs to be earned after thinking a lot. Like, but I don't make this novice mistake. This is a very novice mistake. When I'm teaching to students, sometimes they say, oh, the end state is the invariant. No, invariant has to hold even in the initial state. Invariant holds when the actions take you through everything. So what is that invariant? There has been work on developing inductive invariants automatically. That work is, you know, still not automated, right? They try to look at backsource, etc., but there isn't a still general thing that helps for writing inductive invariants. Maybe that will happen, and that would help here. But then again, invariant actions, monotonicity, protocol design, they all are intertwined, and it's not easy to write invariants. And I also learned the hard lesson through some failed modeling that safety invariants are not enough. You need to write progress invariants to make sure your model is doing something reasonable. One failure mode would be trying to write an LLM-guided invariant and then checking TLA. Oh, it passes, my system is secure, but it wasn't doing anything useful. Write the liveness invariants, write a lot of liveness invariants to make sure that you reach all the states that matter. So again, going back to Lamport-Paxos example, he had different levels of invariance. At the consensus level, very high level, at most one value is chosen. Voting level, chosen is equal to values with a quorum of votes in some ballot, and the lower level, no different values in same ballot, and only one vote, only vote if safe at B. These invariants are tied. You can click on this link to look at his talk, slides, and this derivation. Non-trivial, and they scaffold the refinement chain. They show genuine understanding of why consensus works. In my experience, this happened in 2022 with PowerSet Paxos from Amazon. I was at AWS. Chuck Carman is a principal engineer at Amazon side of the business, where they look at this shipping part of the business, the retail part of the business. He had been thinking of a distributed protocol to make that make a scalable version of how should I explain? Make a scalable infrastructure system. And I don't want to reveal too much because this is not published and this is being deployed. So he first had this intuition, sketch a lot of things in Excel, meaning that, oh, this node has this node, what would a transaction merge? So this sort of marries transaction and Paxos. So Paxos scaffolded transaction, and then, but this is not enough. This is operational, and there could be mistakes, and he couldn't be sure this is working. So this happens again and again, the same pattern. An engineer that's frustrated enough, they learn TLA+, they write a model on their own. There's nobody to help. And then when they get stuck, they reach to a TLA+ expert in the company. And with the little guidance, they continue. So he reached to me when his model had a state space explosion. And I said, oh, this is how you fix it. You don't need the read operations. Read comes from invariants. You don't need an extra read, which is blowing up the concurrence space. And the invariants check that for you. You don't even need that. And then the beauty of this thing is, this is his testimonial he sent to me, is that it then took a week to translate this TLA+ model, which he basically refined even to message passing to translate to code. And then he says that basically 80% of the code was testing invariance. That the TLA+ model he established for this thing. And then the strong part of the testimonial is that he wrote this core model in TLA+, and he taught this to the other engineers, and other engineers, when they are developing other services around this core model, they keep finding bugs, not in the core model, because that's TLA+ model. And then the other engineers says that, you know, why didn't we model the other parts in TLA+ when we started? And then this testing of invariance, Igor's talk said that this could be largely automated. That's very good news. But then, how do you find the invariance? This is the mindset we need to teach with examples to the engineers. So what's the lesson from this? The expensive part isn't writing the algorithm, right? Writing the code is now cheap with LLMs. Writing the algorithm, you know, you can write the algorithm if you are experienced, but there could be corner cases in it. The expensive part is trusting the algorithm. How do you trust the algorithm with TLA+ modeling? Okay. I have 10 minutes, so I'll pick up speed a little bit. Explore through stepwise refinement. Start with the most abstract spec, refine downward. Each level adds detail while preserving the safety from above. Refinement in TLA+ is implication. Concrete behaviors implies abstract behaviors. I believe we can lean on this more. I don't know how to, but I don't see this used in TLA+ models enough. I started using this in recent 3 years or more. I don't know how to make this more user-friendly for people to use. But this is very powerful tool. Going all the way to Nicholas Wirth and Dijkstra, they had this stepwise refinement things. Dijkstra has, in his book, a lot of discussion about that. And the lesson I have here is, I told you that the value of TLA plus is design accelerator. That means you explore the design space with TLA plus as your thinking tool. The lesson I have here is to explore a variant of a protocol, go up in the refinement stack, change it when you are refining back again, try to, and verify this, okay? When you are stuck with this thing, again, go up, figure out another refinement, figure out another way to refine it down one level, and try to verify it, right? This is what happened with the secondary index. The guy was stuck here, kept adding to his design document, go up, figure out another way, explore at that level, go down, and so on. I have 2 examples to talk about here. Well, 3. Lamport's one. I'm going to skip this, okay? But this is beautifully done. My most recent MongoDB one on this was for the rough leases development. We discovered the 2 optimizations. Basically, I started just with a rough model to see what would leases look like here. And then it is high level, but there I realized that thanks to Raph's protocol's strong leader completeness property, we could implement leases much better. So it led me to think at the abstract plane, which we later refine one level down, and we have our protocol. And the lesson here is start modeling early. Don't wait to get design inspiration. Sometimes you get the design inspiration by looking at the abstracting that you start with. Finally, I think this is another model worth teaching to people starting to modeling, is aggressively refine atomicity. People tend to write large atomic actions, and this sweeps concurrency under the rug. You have an inefficient, more locking-based system. The coarse-grained thing could be okay to get an idea for correctness, but then keep splitting, refining atomicity. This is another example of refinement, but in the context of atomicity, in the context of single action. The refined version would give the implementation maximum freedom to reorder and parallelize, and this would be more efficient implementation. And this connects back to the monotonic guards idea. In industry, I saw this for S3, fast copy design. Ernie Cohen did this design. He's very old school. He's one of the gurus who can see the monotonic dimension easily in any protocol. But this came to him because he had been so at a high level abstract plane, and he has like 4 decades of distributed protocol design. And so the problem as part of fast copy was to design a distributed set that once empty stays empty forever. This is simple, right? Can't you check that a set is empty? Not necessarily. In a distributed system, you cannot check that a set is empty because it could be implemented over multiple nodes. Think about a list scan. You need to scan multiple nodes to check empty. And then after you scan it, somebody could write something there. When do you stop the scan, right? So he pushed things to finest granularity and no distributed locking, even with a node. This was basically eye-opening to me because it kept things very efficient. This makes the interleaving surface area explode, but the TLC can verify things without problem. So it's better to do this at the design time to give the maximum leverage for implementation. So the lesson here is push for the finest granularity you can. TLA plus can be used to verify that the interleavings are safe. This is my final one. Share your mental models and TLA plus models. Okay, I found that the TLA plus models are actually excellent communication artifacts. You know, they are not just verification inputs. Its value is in design, and communication is part of the design. So write for humans, use clear action names, explicit invariants. A well-structured spec shows essential logic without implementation noise. Here we can also do better as TLA plus community. Spectacle is a web-based tool. If you click on this, you go there. My colleague, for disclosure, Charles wrote this. Okay, so you can go to Paxos. This is all running in browser. This is not doing model checking, but this is making you explore the state space. And this is like P1. No, node A does P1. And node 0 does P1. I don't have my glasses, so I'm making things up. And you can also like explode things. So per acceptor state, etc. You can go back. You can go forward. You can copy the URL, give it to another engineer over Slack. He clicks on it, and he sees the offending trace from this. It doesn't do model checking, but it's for communication. Example of where this worked was in Amazon Aurora distributed SQL. I wrote the first TLA plus model for the database, detailed one. This became a good communication anchor for the big team. When you are working with a big team, I found that it's basically big challenges to keep everyone in sync across different sub-teams. You have a big team, and the model helps for that. And it sped up onboarding. When you get more engineers, how do they understand the protocol, what we are building? The model gives you non-natural language, more precise understanding at a higher level, and they can play with things to see if we didn't have it, how would this break? I think that's the real value. And this kept everyone aligned on protocol design. Later, when we got help from the formal methods teams in Amazon, I pointed them to the TLA plus models, and they were able to understand what's the protocol and build testing tools around that much easily. Most recent thing on this was with Will Charles, we did a MongoDB transaction modeling. This is modeled after production, like 7 years after production. What's the value of it? This was built, the transactions has been built over many years. And most engineers know only one part of the transaction model, but they don't know the full picture. When we were asking questions about how does this work, they say, oh, the other engineer may know about this. But when you write a model, the documents are not useful for this. The documents are not useful for this because it's a very big complex system and distributed. When we wrote this model, finally, we have a simple, precise way where we can point, okay, this is how the protocols, the distributed transaction protocol work for MongoDB. Our MongoDB distributed transaction protocol spec. This is how it works. And we use the spec to also generate thousands of unit tests to test the storage layer. So the learning from this is it's never too late to model. And one of the purest intellectual pleasures I know as distributed systems person is using TLA plus to reduce a tangled distributed system to a simple essential logic. So to close, as LLMs write more code, I believe TLA plus for design and reasoning grows in value, and we should support people by teaching the mental models to make them use, make the modeling easy on them, or make the modeling create value for them and not become performative things, rather useful things. And I tried to show you that the hardest part is learning what to model, abstraction, what to omit, abstraction, when to trust what the model tells you, what is monotonicity, invariants, and how does refinement help you. This is modeling judgment. I believe it's a skill you can practice and learn, but we need to create material on this. And finally, like AI plus, TLA plus tech for software development is, I think, a really promising idea, and we should be making efforts to make this happen. Like I was mentioning over lunch, I see some JavaScript developer and TypeScript developer. He says, oh, TLA Plus is magical. He writes one-page web apps, and I can use TLA Plus. He doesn't know TLA Plus. With LLMs, he discovered it. He says, I can write TLA Plus with LLMs and, and check my design, the logic of my app before I release it, so I don't have a bug. But he needs these, and maybe that's not a distributed system, so that's easier. That's just concurrency, and LLMs do a better job in writing single-node concurrent models. But we need to help people with these mental models so that they can write effective models. Thank you.